Okay, this is a tutorial on angular motion and torque. So let's look at a problem on angular velocity. We got a merry-go-round accelerated rate of 0.005 revolutions per second squared. Assuming it starts at rest, we want to know the rotational velocity at the end of 1 minute. How many revolutions does it make? Then we'll talk about how many radians it makes, and then what would be the linear velocity at the end of that minute. But what that means is we're going to need some equations of motion related to rotation and not linear ones. The forms are very similar. Our rotational velocity given by the Greek lettering, and so instead of V, you have the Greek letter, and then the alpha for the acceleration is still T for time. And then distance is actually Greek letter theta because you're moving angle and not linear distance. So we got the initial angular velocity times time plus 1/2 the rotational acceleration times t squared. The difference in variables, even though the equations are pretty much the same, will allow you to realize you're talking about rotation instead of linear motion. Regardless, what's the rotational velocity? We're going to use that first equation. The initial velocity is 0 because it's at rest, so that kind of goes away, plus the acceleration times the time. And so then we got acceleration times time, so we got 0.005 revolutions per second squared times the time. 1 minute is 60 seconds. So one of those will cancel. So then we just run that through our calculator, 0.005 times 60. And we get 0.3 revolutions per second at the end of a minute. That's how fast it'll be rotating. So that's answer to part A. Part B says how many revolutions does it make? So then we need the other equation, the theta, omega 0 times t. That's going to cancel again because the initial velocity is 0 plus 1/2 acceleration times time squared. So 1/2 that acceleration times the time squared, which would be 60 seconds squared. So 0.5 times 0.005 times 60 squared gives us 9 revolutions. Now, what does that mean in radians? We need to understand the unit circle. And I'm going to bring in an extra piece of paper just to show you the unit circle for a second. So if we got our circle, we're going to split it into 4 quadrants. So if we start at 0 degrees here, that'll be 90 degrees. This will be 180 degrees. This will be 270 degrees. And then if we make it all the way around, that'd be 360 degrees. Now, if we did that in radians, we'd, of course, be at 0 here. But then it's going to be pi over 2 radians there, pi radians here, and 3 pi over 2 radians there, and then 2 pi radians if you make it all the way around. Now, what's important there to realize is that we're making complete revolutions, so there'll be multiples of the 2 pi. And so 9 revolutions would be 9 times 2 pi, or 18 pi radians, which would be our answer to part C. If we come back over here, we're going to say C, and we worked it over here, but we're going to say, well, 18 pi radians. Now the last part, part D, we want to know the linear velocity. If this is the angular velocity, what's the linear velocity? The linear velocity is going to be equal to the radius times the angular velocity. And so you'd need to know the radius of the circle. We'll say that for our purposes, this radius is going to be 2 meters, just so we have a radius to use. And then so the radius will be 2 meters times the 0.0 or 0.3 revolutions per second. And so 2 times 0.3 would be 0.6 meters per second. And that would be the linear speed. Now, oops, stuck together. So then we got torque. Torque is a function of having torque is given by tau equals the force times the length of the lever arm, which is useful for a wrench. So the length here would be the length of the lever arm, and the amount you apply at the end of the handle is the force. But it depends on where you grab it. If you only grab it here, then your length of the lever arm is less, and therefore your torque is less. So in this case, the torque, if we apply a 50 Newton force, we got 50 newtons. And length of the lever arm is 24 centimeters, 0.24 meters. Now, as a general rule, clockwise motion or rotation to the right, that is rotation this way, which is the way that wrench is going, is negative. Rotation going around in a counterclockwise direction is considered positive, or rotation to the left. So in this case, this is rotating clockwise, and so that would be negative. So 50 times 0.24, or 12 Newton meters. So that would be part A. So B, what would the torque be applied if it were halfway up? So halfway up would be half of that length. So guess what? The torque's going to be half as much. The torque is equal to the negative 50 newtons times 0.12 meters, or 6 Newton meters, half as much, which is how far you are away, or the length of the lever arm is very important to how much torque you get. Now in this case, we've got two forces acting in opposite directions, radius 1.2 meters. So we know the torque due to the 80 Newton force, which will produce a counterclockwise rotation, and the 50 Newton force, which will produce a clockwise rotation. So for A, the torque is equal to FL. So it's going to be an 80 Newton force applied at a distance of 1.2 meters. or 96 Newton meters. And then B, that torque will be a 50 Newton force, again over 1.2 meters, which will be 60 Newton meters. Now you got two choices really. You could subtract the forces since they're being applied in equal directions, or just subtract the torques to get C. So C will be the difference in those two, which will be 36 Newton meters. Which way is it rotating? The bigger force is going in a counterclockwise way, so the net torque will be in the counterclockwise way. So if we give these signs, remember the clockwise rotation was negative, so this is negative, and so we end up with a positive overall rotation, indicating rotation in the counterclockwise way. And this has been a brief tutorial on angular motion and torque.